Good evening, everybody. My name is Roberto Sainz, and I will be talking about my exam 3 for my process and control class at UT Tyler UT Tyler. The first question we had was to design an inner loop controller as a PI controller. The second part was to design an outer loop as a PI, and then plot the disturbance and the rejection response of the following thing. These are the transfer functions of the controllers that we were given. So here I input the code into the MATLAB. You can see the transfer functions there up at the top, as well as to the right. And that left us with a critical uh, gain, a proportional gain of 2.15 e to the negative 5, and integral time of 5e to the negative 4. That was going to be for the inner loop. For the outer loop, we have a proportional gain of 14.7 and an integral time of 286. Here we plot the disturbance. The cascade loops achieves its task of disturbance rejection, and the response offset between the two controllers is 0.1, 0.1. For the second problem, we had this combined feedback and feed forward control system. Uh, for the first part, we were asked to find For the first part, we were asked to find the closed loop transfer function if there was zero disturbance. So since there's no disturbance, the entire top part of the transfer function cancels away. To analyze the transfer function, it's g forward plus over one plus loop. Uh, Forward over one plus loops gives us this equation right here: Km GC GV GP over the loop 1 plus GC GV GP GM. There's that equation again. We are solving for the characteristic equation to try to find the gain of the controller, Kc. So here, these are our values given to us on the right, and then you can see them substituted in on the bottom. We converted GC equals Kc, the gain, because we're going to use that to pump in the direct substitution method in order to find the controller. So after plugging in those previous equations, substituting Kc for Gc and working out the math, we are left with 13.5 s cubed plus 67.75 s squared plus 55.25 s plus 1 plus 128 e to the negative 6 s Kc. We substitute Iw in for s. We get, which gives us the equation below that. We get our real part of the equation and our imaginary part of the equation. We have there's only one unknown variable in the real portion of our equation. So we find omega, which is equal to 0.121. Knowing omega, we can plug it into the imaginary part of the equation to try to find Kc. After doing all the math, I ended up with an imaginary number over a complex number, and my mathematical abilities didn't let me pursue any farther. I did try I was looking into Euler's method and another one, but that I have nothing to show for. So that brings us to our third problem. The question was, why would an engineer choose a combined feedback and feed forward controller? Implementing a feed forward controller onto a feedback controller makes many improvements over the overall design. One of them is that in an ideal environment, the feed forward, it is already programmed to anticipate a certain disturbance, and therefore it can compensate for the disturbance without there being any effect on the output. So say you're coming up onto a hill and your car knows you're coming up onto a hill, so you never lose speed. It automatically gave the engine more power before you even hit the hill. So no matter what, you're always going 70. It never dropped down, had to drop a gear, whatever. It already did that for you. Another benefit of using a feed-forward controller is that since it can anticipate these disturbances, it can gradually take it into effect. So it's not just trying to make it go right away. It can slowly build up, which makes less wear and tear on your equipment. These are a reference that I used for the equation. Thank you.